Hi everyone, welcome to our last week of calculus. So during the previous week we were focusing on the definite integral, and this week our main emphasis will be on the indefinite integral. So remember, the definite integral gave us a number as the answer, whereas the indefinite integral gives us a function or a set of functions. So let's start with this word problem here, because we like to look at things in context. So at a time t equals 0, the population of some region is 9,000. And we know its rate of change over the next 6 years is given by this function, that many people per year. And the question is, what is the maximum population on this interval from 0 to 6? So we've done a lot of problems this year where we have found the maximum of something. And in all of those cases, what was the first step to doing that? In all of those cases, the very first thing we did was we took the derivative. So is that what we should do here? Should we take the derivative of this function and look for its critical points where it's 0 or undefined? What do you think? I hope you think no, because remember, now that we are doing the inverse problem, we are starting with the rate of change. So this is already the derivative. So if we were saying that p of t is the population, we already know p prime of t is this. So we don't need to take the derivative. We've already got the derivative here. So we have p prime of t equals this function, negative 300 t minus 1 t minus 5. So this is the function whose derivative we want to, this is the function we want to set to 0. So if we set this equal to 0, there are two solutions here because we were given it so nicely factored. That gives us either t equals 1 or t equals 5. So these are our critical points. These are the candidates for being local extrema. So thinking back to when we used to do the sort of thing where we were doing differential calculus, what is our next step to do to decide what we've got here, maxima or minima? This is where we would do our number line, right? So we can put these two values on the number line, t equals 1 and t equals 5, and p prime and p. And back then, we were always careful not to plug into the wrong function, right? We want to be plugging values into what now, p or p prime? We want to be plugging into p prime because we want to know whether the slope is positive or negative. Back then, there was the danger because we actually had the function p, and we had then computed p prime. Now there's no danger. We only have p prime, so there's no chance of plugging into the wrong function here. So we got to pick a number out here. Good choice would be 0. If we plug in 0, we get a negative times a negative times a negative. So I think 3 negatives gives us a negative. So what does that tell us about the population out here? If p prime is negative, we know p is doing what? We know p is decreasing. And if we plug in a value between 1 and 5, like 3, we'll get a negative, a positive, and a negative. And that should give us a positive. So we see that t equals 1 is a local minimum, which is not what we're looking for here. We're looking for a maximum. And now we got to pick a number out here. So 6 would be a good choice. And we'll get a negative times a positive, which is a negative. So does that mean that our maximum population is guaranteed to be at t equals 5? What do you think? Is it absolutely certain that the maximum will be at t equals 5? If you think back to when we came up with our rules for finding the global maximum and the global minimum, they might occur at a local maximum or a local minimum, but where might else they occur? They might also occur at an endpoint, right? So this graph is somehow starting here, comes down to t equals 1, comes up to t equals 5, and comes down again to t equals 6. And our question is, which point is higher here? Is the value higher? So we know that the maximum might be at t equals 5, but where else might the maximum be? It might be at this endpoint back here at t equals 0. So we want to compare which of those is the higher y value. So in the old days, when we were given, starting with the function f, and then we took f prime and did the number line, what we would next do is plug the numbers 0 and 5 into the function f of x and compare the y values. But so now this is where we actually have to do a little bit more work now. Here we started with the derivative, so we need to go back to find p of t. So we see from this that the maximum must be at one of these 2 points, t equals 0 or t equals 5. And we need to find p of t. So we got the derivative for free here. But now we need to do the work to get back to the original function for the population. But we know how to do that. So P of t will be the antiderivative of this. Now the way this is written out isn't so nice, so we might like to multiply that out. But let's just write for 1 second here. It's the antiderivative of f of t dt. So if we multiply this all out, we're going to get t times t is a t squared with a negative 300 out front. And if we FOIL this all out, we get a negative 6t in the middle. We multiply that by negative 300, we get an 1800t. And at the very end, we get a 5, and we multiply that by negative 300, negative 1500. So if we're trying to find P of t, this is the function we need to find the antiderivative of. So here we just use our rules for the antiderivative, our constant multiple rule and the power rule. So this is going to become negative 300. We're going to add 1 to the exponent, so t cubed over 3, and the 3 will cancel with the 3 and the 300. We should just get negative 100 t cubed. When we take the antiderivative of this, this is t to the first power, so we get 1800 t squared over 2, so that's going to give us 900 t squared. And the antiderivative of negative 1500 is 1500 t. Now, is this the only antiderivative that this could possibly be? As we've discussed many times, it's not, right? We have to put a plus c here at the end. Do we have enough information to figure out what the value of c is for this particular problem? Or do we have to leave the c in there? We do have enough information, right? We were told that at time 0, the population is 9,000. So we know that P of 0 is 9,000. So if I plug 0 into this, I've got to get 9,000. So negative 100 times 0 cubed plus 900 times 0 squared minus 1500 times 0 plus c has got to equal 9,000. But all of these terms just become 0, and so we see that the c is going to be 9,000, right? In this case, because this was all of these were just power functions, when we plugged in 0, we got 0, and the c ended up being the value at time 0. But let's be careful. That's not always going to be the case. For example, if this had been 900 times e to the t, when we plugged in 0 here, we would have gotten 900 times 1, and then we would need to figure out what c was appropriately there. But this tells us that P of t, we now have the formula for the population at any time. And the point in doing that was so that we could compare the population at time 0 to the population at time 5. And the population at time 0, we already know, that was 9,000. And if you plug in 5 to this, we won't go through all of the arithmetic there, but if you plug in 5, we'll get 11,500. So our two candidates were time 0 and time 5, and we figured out that time 5 was the bigger population of the two. And the question actually said, what is the maximum population? It didn't say at what time does it occur, so therefore our answer is that the maximum population is 11,500. That's the highest this population ever gets. So this is similar to the problems that we did before, where we were trying to find a max or a min, except that now we were starting with the derivative instead of with the original function. Question part B is going to be to find the minimum population. So before we change the board, let's look at this number line and see where is the minimum population going to have to be. Give yourself a second, decide where you think that's going to be. Going to be two choices again, right? The min might be at time 1, or it might be at time 6. We're going to have to figure out the compare the two y values at those points. So what's the minimum population? Again, on this interval from 0 to 6. So from the number line, We already know what the two possible times are for that to happen. Minimum is at t equals 1. That was one of our choices. Or at the far end point, or t equals 6. So how will we decide which it is? We'll do the same thing as we did to find the maximum. We want to compute p of 1, and we want to compute p of 6. And as usual, let's try to think about what a reasonable answer is in advance so that we know what we're more likely to find out if we made a mistake. P of 1 should definitely be less than what number? It should be definitely less than 9,000, right? Because if you look back at the number line, the population at 0 was 9,000, and we decreased until time 1. And in fact, P of 1 is 8,300 if you plug 1 into that formula that we just came about. What about P of 6? P of 6 should definitely be less than what number? If you look back at the number line, the population decreased from time 5 to time 6. So P of 6 should definitely be less than the population at time 5, which was 11,500. And it is. P of 6 is 10,800. So what's the answer of these two? The lower was 8,300. So that's the minimum population. All right, let's ask two more questions about this particular problem here. Let's find out what the average rate of change of the population is on this same interval. And there's an easy way and a hard way to do this one. Because you'll remember, average rate of change is a concept that we've had all the way back since week 3. Even before we knew the derivative, anything about derivative, about instantaneous rate of change, we had a way of computing the average rate of change, right? If we wanted to find the average rate of change of some function, we just took the change in the y value over the change in the x value. So in this case, the average rate of change on this interval, we want to figure out how much the population actually changed. So what was the ending population? That's P of 6 minus what was the starting population over 6 minus 0. Now these are numbers that we already know, right? P of 6 we know is 10,800. And P of 0 we knew was 9,000 over 6. So that's on the population gained 1,800 people during these 6 years. 1,800 people in 6 years is 300 people per year. So that was the easy way to do it, right? Since we already had the values of P of 6 and P of 0. But our very last interpretation of the definite integral from last week was as the average value. And we could make that the average value of any function. So from last week, we could have said that if I want to find the average value of the rate of change, what we do is this. So from last week, the average value of the rate of change, that's the same as saying the average rate of change. Average value of the rate of change is the average rate of change. How did we figure out last week to do that? We took 1 over 6 minus 0, and then the integral from 0 to 6 of the function whose average value we were looking at. And in this case, the function whose average value we're looking at is p prime. So this is 1/6. And now here we use our fundamental theorem, right? So it says find a function whose derivative is p prime. Well, what function's derivative is p prime? That's p. So that's p of t evaluated from 0 to 6. And I hope you're starting to see that this is going to give us exactly the same answer. P of 6 minus P of 0, which is going to be 300 people per year that way as well. So the fact that we already knew the value of P of 6 and P of 0 meant that we didn't need to go through this trouble of finding any antiderivative. But now, the last part, part D, we'd like to actually find out what the average population is during this time. So what's the average population? Not the average rate of change, the actual average population. So we talked last week about how you might try to do this in practice. You might just sample it at a whole bunch of different times, add them all up, and divide by the number of times that you sampled. We were talking about temperature last week. But we said that if we want to get the exact value of that, we let the number of times that we sample it go off to infinity, and then we get something that involves an integral. So from last week, this is supposed to be 1 over 6 minus 0, the integral from 0 to 6 of the actual population function. So is there any shortcut way for this one? Or do we really need to go and do some work now? Unfortunately, we do need to go and do some work because we don't have an antiderivative of this population function yet. So we need to say 1 over 6, integral from 0 to 6, of the function p of t that we found up above. So negative 100 t cubed plus 900 t squared minus 1500 t plus 9,000. Just pretend that dt is on the same line as everything else. And now we use our power rule and our constant multiple rule to find all of these antiderivatives. So let's do that. So negative 100 t cubed will become what? Negative 100 t to the 4th over 4. And the negative 100 over 4 will just give us 25 t to the 4th. 900 t squared will become 900 t cubed over 3. And the 900 over 3 gives us a 300 t cubed. And then the 1500 t will become 1500 t squared over 2, which is minus 750 t squared. And finally, the 9,000 gives us 9,000 t. And do we need to put a plus c here? We could if we wanted to, but we don't need to, as we've discussed earlier, because we're doing a definite integral. So if we put some plus c there, we're going to plug that in for the 6 and then plug in for the 0 and subtract, and the c's will cancel. So there's no need to put it there. But again, if you feel like putting it there, go ahead. Nothing will go wrong if you do that. So then we're going to have to plug everything in here. This won't be the most exciting part of the class today. We should start to think about what a reasonable answer is here, right? What should the answer be between? Definitely between what two numbers? So when I plugged in the 6's, that's what's going to happen. When I plug in the 0's, everything's going to be 0. So I'm just going to write 0 plus 0 minus 0 plus 0. Well, we know that the population was never more than 11,500. In part A, we found the maximum was 11,500. In part B, we found the minimum was 8,300. So definitely the average had better be between those two numbers. And in fact, it is. When we go ahead and do the arithmetic for this, we get 9,900. Now, what are the units on this? We talked about this again last week when we did average value, but let's do it one more time. We found the area under the p of t function is what we just, that was our integral here. And the p of t function looked something like this. Started at 9,000. And we found the area under that. So what are the units of the p of this area that we've just found? If we look at some rectangle from our Riemann sum, the vertical units are measured in what? They're measured in whatever these units are. So the units here are people times the horizontal units, which are in years. So people years are the units. If I don't have this 1/6 here, the units of this integral are people years. So people years you might not have ever heard about if you're doing insurance, although actually the actuaries deal with people years all the time to estimate how much to charge, for example, all the people in your company, what to charge for health insurance or life insurance. But often what we hear, it's probably not the appropriate thing to say, we're supposed to say person hours instead of man hours, as people used to say. But if some job takes 40 person hours, what does that mean? It means it takes one person 40 hours, takes 2 people 20 hours. It takes 5 people 8 hours each. That's what a person hour is. So you can think about a people year or a person year in the same way. But we didn't expect to have units of person years here or people years. We expected to get units of just people. And why did that happen? That came from the 6 minus 0, because the 6 and the 0 are measured in years. So this was in people years, this was in 1 over years, and therefore this was in people, just as we expected. We have a check your understanding for you to go and try to do one of these on your own, and then we'll come back and do something with sketching antiderivatives.